this video, we will see magnetic field due to toroid. So this is also an application of Ampere's substitution theorem. So far we have learned due to magnetic field due to a straight current carrying conductor and magnetic field due to solenoid. So toroid, what is solenoid? Straight wire bound in the form of spring. Now the same spring, when you are closing on both the ends, like we have a straight conductor made in the form of solenoid in this way, right? Now for toroid, we are bending it, and solenoid turned in the form of a circle is a toroid. Current in, current out. I think. Okay, now we are considering we have to find the magnetic field here, that is outside the toroid, then inside the toroid, then passing through the centers of the coil, that is within the toroid. Now see, current is going in this direction, so what will happen in the loop? Current goes and upward, downward, then upward, then downward. So here current comes, then into the plane, then coming out, into the plane, coming out. So current goes in this direction. Out, in, out, in, out, in. So this, if you are cutting and marking as a point, then we can see current going into, then to the other side coming out, then into, then coming out. So into, so I will mark a circle. So here also, here all the points coming out. So I'm just cutting and seeing the cross section and how does the current goes. I will explain it to you once again. Okay. Let's say the current entered, gone into the plane, then coming out into, coming out. See, this one. From here, it is coming out. Okay, so first point outside the solenoid. Outside the solenoid. So next thing is inside solenoid. Sorry, this one is toroid. Toroid. Out, inside toroid. Out. This is in, within. So don't get confused. I meant by inside as a condition like this. See, inside of the toroid, outside and within the toroid. Now outside the toroid, this one is my Amperian loop. Okay, now when I am considering an Amperian loop in this direction, what is the net current entering the plane? See, let's say current I enters, same current leaves, next current enters. So I enters, leaves, I enters, leaves, I enters, leaves. So total current, if you are taking all entry points, all exit points, if you are adding them, it will be 0. So outside, integral B dot dl is equal to mu 0 into I, but I has become, net I becomes 0, so this value is 0, which means B in the integral dl. So a number, see, integral dl anyway cannot be 0, that is the total length, that is the perimeter, right? Here the perimeter. So a number multiplied by a non-zero value, if it is 0, this number is 0, which means B is equal to 0. And inside, it is very simple. Through this loop, through inside, is there any current entry? Is there any current exit? No, it's 0. So through this loop also, magnetic field will be 0 because current is 0. So B dot dl is equal to mu 0 into I, which is 0. Since I is equal to 0, means B is equal to, implies B is equal to 0. So here, why the magnetic field is 0? Net current is 0. Entry, exit, entry, exit, entry, exit. Same current enters, same current leaves. But here there are no current entry, no current exit also. Now this point is very important. Okay. How to get the value of magnetic field within the toroid? We have to consider an ambiguous loop that has the point within the toroid. So this is the ambiguous loop. Now apply Ampere's circuital theorem. What is that? Line integral of d dot dl is equal to mu 0 into I. Now inside this ambiguous loop, what is the total current entering or leaving? Yeah, all the current in each and every loop of this toroid is entering inside. Okay, but current is coming out, but not through the loop. It is not threading from the loop. Only the current are threading into the loop. Okay, going in, going in, going in, going in. Coming out is there, but it is outside the loop. So I can consider all the currents. So the value is equal to mu 0 into how many numbers of turns are there? Capital N number of turns are there, and if current in each loop is I, this will be the value. So B magnetic field at all the point will be constant in the point because there is a symmetry. So I can take B out. So D into B. Now line integral of dl is equal to mu 0 into capital N into I. So what is the line integral? That is the total length of this toroid. Okay, the total length, all the points. This one, the total length of the loop basically. So if the radius is A, then that will be 2 pi A. So D into 2 pi A is equal to mu 0 into Ni. Now I can keep B here and mu 0 Ni transfer 2 pi A to the other side, 2 pi A. But one thing is 2 pi A is the total length of the toroid, right? N is the total number of turns. So N by 2 pi A can be taken as number of turns per unit length, that is small n. So mu 0 small n into I, where N by L is N by 2 pi A, which is equal to number of turns per unit length. So it's the same value, but the thing here is now the magnetic field is circular. There we got a magnetic field in this way. Now here the magnetic field direction will be in this way. It will be forming a loop within itself. But here the loop will be formed in this way. Magnetic field lines will be forming a closed loop that will be from north to the south here. But here it will be within itself. So that is the third application, the last application of Ampere's circuital theorem. Thank you.